Hi ladies, this is lesson 2.6. It's about scatter plots and finding the line that best fits the graph with all of your scatter plots. And a scatter plot it's a graph, just like our linear graphs that we've been making, but it doesn't show a full line. It just shows a set of data pairs, X and Y, so a few different coordinate pairs. The next vocab term we have is positive correlation. And a positive correlation within your scatter plot is when y tends to increase as x increases. And a negative correlation is when the data in your plot, your points, when y tends to decrease as x increases. So in this chapter, our goal is to fit lines to data in scatter plots. So our scatter plots, again, are just a set of data pairs. And then our correlation coefficient, we're going to refer to as R. And this is a line that we're going to draw. And the correlation coefficient refers to how well this line fits our set of data pairs. So again, our data pairs are not going to be perfectly linear like in the models we've been working before. But our correlation coefficient is going to be between -1 and 1, and it's going to measure how well our line fits our data pairs. And our last vocabulary term is the best fitting line, and often we can model this just by graphing and finding a line that's close to as many data points as possible. The best fitting line is the line that lies as close as possible to all of our data points. On your guided note sheets, you can see this snip from your book, and it again just outlines the vocabulary terms that we discussed on the first slide. But here you can actually visualize positive correlation, negative correlation, and approximately no correlation. In the first one, positive correlation, you can see pretty easily that as your x's increase, your y's increase for each point that you've plotted. And for the negative correlation, you can see the same thing. Here's our positive correlation. For our negative correlation, we can see the same thing. As our x's are increasing, so again, our x's are increasing, our y's are decreasing. So for the last one, approximately no correlation, it's really hard to tell where the best line would be, whether it goes up, rises, or whether it falls. And then we see our correlation coefficients. Again, we refer to our correlation coefficient for our linear regression line as R, and it's a number between -1 and 0. And sorry, -1 and +1. So in the first example, it says estimate correlation coefficients. For each scatter plot, describe the correlation shown and tell whether the correlation coefficient is closest to -1, -1/2, 0, 1/2, or 1. With our correlation coefficients, this first one, -1, says that there is a strong relationship between x's and y's, and the slope is negative. Here, we have -0.5 as our R, our correlation coefficient, and that shows that there's a correlation between x and y, and the slope is negative, but it's not very strong, meaning the line, the best fit line, is not going to be a perfect line right next to all the points. 0 means that there's no correlation, or a very, very weak one, if anything. 0 means there's no correlation between x and y. 0.5, there's a positive correlation between x and y, so when x increases, y increases. And 1 means there's a very strong correlation between x and y. So as x increases, y increases almost by exactly the same amount. So the closer you are to -1 or 1, the stronger your correlation between x and y is. So strong correlation and negative slope. Negative 0.5 is weak correlation between x and y, and it's a negative slope. 0, no correlation between x and y. 0.5 is a weak correlation between x and y, and it's a positive slope. And 1 is a strong correlation between x and y, and it's a positive slope. So the slope I'm talking about is the slope of the best fit line. So on the first one, you can see that there's a correlation between x and y, and actually that line I drew probably wasn't quite the best fit, but somewhere around there. When you're drawing the best fit line, you want to make sure that there's about the same number of points below the line as there are above, so that you can get your line closest to as many points as possible. So we can see that there's a negative correlation, but it's not super strong. So to estimate, we would say about -1/2. On letter B, just looking at it, it's hard to tell whether the best fit line would be here or if the best fit line would be here. So for B, we're going to say that it's probably pretty close to 0. It's hard to tell if there's a positive correlation or negative correlation. Doesn't really look like there's much at all. And then letter C, all of our points are pretty close together. So we can see a pretty strong relationship between x and y. And our slope is positive. So we can estimate that correlation coefficient at about 1. Now, if you actually do these, and I'll show you how in just a couple minutes, but letter A, if you actually compute this, we get our R, our correlation coefficient, is about -0.46. For letter B, we get -0.02, so that's pretty close to 0 for our correlation coefficient. And then for the third one, we get R is about 0.98. And actually, I should be using the approximately equal sign since it's not exact. So 0.98 is pretty close to 1, -0.02 is pretty close to 0, and letter A, -0.46 is pretty close to -0.5. In this next part, in order to approximate a best fitting line, the first thing we need to do is actually plot our data points. So we need to draw a scatter plot of the data. After we draw our scatter plot and we see scatter plots similar to the ones on the previous slide, A, B, and C, those are scatter plots. We need to sketch a line that looks like it follows mostly follows the trend given by our data points. So again, we should have about as many points above the line as we do below it. Then we're going to choose 2 points on the line and estimate the coordinates of each of those points. So these points do not have to be original data points. These will be points on the line that we drew that looks like it's about the best fit. And then lastly, we're going to write an equation of the line that we drew that passes through the 2 points that we did in the previous step. So here we're going to approximate a best fitting line. So we've plotted these points. 1, 722. The second point, 2, 763. So all of these points are plotted on our scatter plot. And then we drew this line that looks like it's the best fit. There's about the same number of points below it as there are above it. It looks like it's as close as we can get to all of those data points. Now we need to choose 2 points on our line and then write an equation for that line. So I'm going to choose 2 points that I see on my line. And the first one I'm just going to choose points that are easy to read. So the first one I'm going to choose is point 2, 750, because it looks like it goes right through that point. And then the second one I'm going to choose is point 4, and it looks like it's a little over 800. So I'm going to say it's about 805. So here's my 2 points, 2, 750, and my second point, 4, 805. So first I'm going to find my slope. So again, my slope formula is y2 minus y1 over x2 minus x1. And when I compute this out, I'm going to use this as my second point, and this is my first point. So I get 805 minus 750 divided by 4 minus 2. And for my slope, I get 55 over 2. Then, since I don't quite have an exact y-intercept, I could estimate by looking at my graph, or I could use my point slope form. So I'm going to use point slope form to get my equation for my line. And I can just choose one of these points. I'm going to choose point 2, 750. So point slope form again is y minus y1 equals slope times x minus x1. So we need our slope and we need one more point on the line. So y, and again, I'm going to use point 2, 750. So y minus 750 equals my slope, 55 halves, times, times my x minus 2. Then I'm going to solve for y approximately equals. So my next step, I have y minus 750, and then I distribute out the 55 halves to the group x minus 2, and I get 55 halves x minus 55. Then I can isolate y by adding 750 to both sides, and I get y equals 55 halves x plus 695. So if I look back up at my line, that looks like it might be about where my y-intercept is. Maybe it's off a couple number of people, but it's pretty close. And that's all our linear our best fit line is, it's going to be pretty close. So actually I should use y approximately equals, since I don't have exact data points for my line. Once I get a best fit line, really the purpose of having a line like this is to make predictions for the future. So I don't have data points for future games. The last one I have is game 7. So I know how many people attended the 7th football game, but I don't know how many people attended the 8th game or the 9th game or the 10th game. So that's really why I would like to use a best fit line or this linear regression model, so that in the future I can estimate how many people are going to come to the game. So it says use the equation of the line of best fit from example 2, the one we just did, to predict the number of people that will attend the 10th football game. So if I look back at my regression line, I said y approximately equals 55 halves x plus 695. So if I'm estimating how many people would attend the 10th game, that is my x coordinate, and y is the number of people, I can substitute in 10 for x. So I get y approximately equals 275 plus 695. So my estimate for the number of people is 970 people will attend the 7th football game. So on your guided note sheets, you see a couple examples that are not completed. So please try these on your own, similar to the ones we just did together. Please pause the video while you work and then unpause for the solutions. On the first one, it says tell whether the data has positive correlation, negative correlation, or no correlation. And then part B says tell whether the correlation coefficient is closest to -1, -1/2, 0, 1/2, or 1. So for the first one, we can see that it's pretty strongly correlated. Every time our x goes up, our y goes up. So this is pretty close to 1. There's a positive correlation. We'll say r approximately equals 1. There's a positive correlation if it's strong. The second one, it's really hard to tell. It goes down and then it goes way up and then it goes down, then it goes down, then it goes up, then it goes up. So I'm going to say that R is pretty close to 0. So it looks like there might be a slightly positive correlation, but pretty close to no correlation. And in the third example, again, you have this on your guided note sheet, so please try this one on your own. So first you'll have to plot the data points and then approximate the best fitting line. So you will draw that in and then write an equation for that line by picking 2 data points and finding the slope and then writing an equation for that line. And then after you have an equation for your best fitting line, use that equation to predict test scores for the 9th test that the class will take. So please pause the video while you work and you can unpause for the solution. So the first thing you'll have to do is plot the data points, and you can see to the right the data points that I have plotted. The next step is to sketch in a line that looks like it's the best fit, meaning that there's the same number of points on top of the line as there are below. and it's as close as you can get to all of the data points. So below you can see the best fit line that I've sketched in. It's got 3 points above and 3 points below, and it's pretty close to all of the data points. It might even be maybe a little bit closer like this. So next I'm going to use my line and look at the line that I've drawn in, and I'm going to pick 2 points on that line. The 2 points I'm going to choose from my line are 284, which is right here, and then 589, which is about right here. It might be a little smaller than 89, but it's pretty close. So now I'm going to use those 2 points to find the slope of my line. So down my line, 2 minus 1 over my x2 minus x1. And my y2 is 89, my y1 is 4. My x2 is 5, and my x1 is 5 minus 2. So I get my slope at 5 over 3. So now I can use the slope to write an equation for a line. And again, I'm going to use point slope form. 5 minus y1 equals slope times x minus x1. I'm going to use just my first point here. So y minus 84 equals 5/3 times x minus 2. Equals 5/3 x minus 10 thirds. Add 84 to both sides. And I get y approximately equals 5/3 x plus 80 and 2/3. Now the next question is to predict the test score for the 9th test that the class is going to take. So again, I have data points all the way up to 5, but my 9 is going to be somewhere over here. So something around here. So just so you can visualize it, just to make sure that your line actually makes sense. So to do that, I'm just going to use my equation where I have y approximately equals 5/3 x plus 80 and 2/3. And I'm going to substitute in 9 for my x. So y approximately equals 5/3 times 9 plus 80 and 2/3. And I get y approximately equals 15 plus 80 and 2/3. And y approximately equals 95 and 2/3. So if I'm looking for my average class score, 95 and 2/3, average class score would be about a 95.67%. Or points out of 100, or points total. It doesn't necessarily say what unit they're measuring average class score in, but my average class score is going to be about 95.67. So if you have any questions, please jot those down. We're going to spend an extra day on this too because I'm going to show you how to use your calculator for best fit lines, and we'll do that in class together. Thanks, ladies.